So I'm going to talk a bit about how some of these smaller monomers could have formed in geochemical systems, and in particular, we're very interested in understanding how the gradients of redox and pH can affect what distributions of products you get from a very simple reaction. And so we're focusing here on these small molecules that are formed from carboxylic acids like glyoxylate and pyruvate. And I have a picture here of Mars because it's a very iron-rich planet. It's got a lot of iron minerals and possibly redox gradients below the surface. And so this was meant to be kind of an analog for stuff that might be happening not just in seafloor systems, but also perhaps in surface systems. So we're looking at the iron hydroxide minerals and the iron oxide minerals. These are minerals that are very reactive and also prone to absorbing ions. And these can vary from a very reduced mineral like green rust all the way to iron oxides and oxyhydroxides that are mostly ferric. And when you have a gradient of redox in these iron mineral systems, you can get a bunch of different mineral phases that all have slightly different reactivities. And this could represent, for example, a seafloor system where the seafloor is a little more oxidized, and as you go deep, it gets more reducing. It could also represent this hydrothermal vent analog, where you have fluid coming up that's more alkaline and reducing, growing chimneys or making sediments that could be more oxidized on the exterior. And then it could also represent subsurface gradients on Mars, for example, or on the early Earth. And so the reaction that we are interested in and seeing how it is affected by redox gradients is reacting these simple organic acids with ammonia, which can be sourced from various geochemical mechanisms, and then seeing what happens when we react this with ammonia in the presence of minerals or just an aqueous solution. And so each carboxylic acid, if you react it, can give you a specific amino acid or a specific alpha hydroxy acid. So pyruvate could give you alanine or lactate and/or lactate. Glyoxylate can give you glycine or glycolate. And so in a system with both precursors, you could get a mixture of all these, plus other compounds as well. So when we do these reactions, we basically start out with a bottle where we make the mineral. So this is an aqueous system. We precipitate a mineral in situ. So this way, it's not a field sample where there's contamination possibility. It's actually a mineral that's freshly formed in the lab, which also keeps it a bit more reactive. And so these are reacted at a temperature, usually around 50 to 70 degrees Celsius. And then the liquid phase is analyzed after these organics are added for a period of time. And we analyze them with various techniques, but mostly proton NMR, which gives you peaks for each compound. And you can correlate the area of the peak to the concentration of that as it's increasing or decreasing with time. And so what we looked at first was what happens in aqueous solution, so no mineral present, and we generally see that pyruvate does not react at all. So pyruvate is kind of less reactive than glyoxylate, and in aqueous solution, we see that glyoxylate does react to give you some glycine, but generally not much of the alpha hydroxy acid. But when we look at the effect of minerals, we basically see that including the mineral really accelerates the reaction that you're getting anyway, but it's just much faster and you get more product forming. So over about 21 days, some glycine will form in this system with no mineral, but when you add mineral, you get a lot more glycine a lot more quickly, plus you get the alpha hydroxy acid in a pretty high yield. And so this was published recently in PNAS, and we're looking at the effect of the overall redox gradient of iron on the reactions of pyruvate in a system. And so we found that when the iron minerals are completely oxidized, you basically get no reaction at all. And then when the minerals are completely reduced, you don't form any amino acid. Even though there's ammonia present, you form just the alpha hydroxy acid. But there's kind of a sweet spot in the middle where you get a maximum of amino acid formation. And in this case, it tends to outcompete for the alpha hydroxy acid. So that's the case of pyruvate. And when you do the same reaction with glyoxylate, it's kind of a similar, but not completely the same result. So you tend to get, again, more alpha hydroxy acid, which is a reduction happening when the mineral is more reduced. But when you have a more oxidized or kind of half-oxidized mineral, you can get both products, but their relative abundance is changing based on which precursor you started with. So that's the important thing. Here, the amino acid kind of dominates at intermediate redox state, and here, the alpha hydroxy acid and the amino acid are about even. So we looked at this a bit more for glyoxylic acid, where we vary the amount of ammonia in the system. Generally, more ammonia makes more amino acid, which makes sense. And then if you go to a more reducing versus a more oxidizing mineral of iron in the system, you just make more glycolate, but the amount of glycine kind of stays the same. So there's a bunch of gradients that intersect here. You have redox, there's also pH, which I don't have time to show that data, and then there's this ammonia concentration gradient, all of which could coexist in a sediment column. So what we're looking at is kind of a system like this, where even though you have just 2 precursors and just 4 plus some minor products, you have a pretty complicated reaction network that's possible here. So if you have, say, an ocean floor, or let's say some hot spring floor or something where you've got minerals, and then as you go deeper, they get more reducing, you can get all sorts of different combinations of things depending where in that gradient you are. So if you're in just the aqueous solution, you might not react pyruvate at all. You might only get glycine from glyoxylic acid. But then as you go a little bit deeper, you can get all the products. If you go really reduced, you're just going to get the alpha hydroxy acids. Another way to look at this is that if you kind of think about it on this axis of redox and pH, so in a reducing iron system going to an oxidizing iron system, in an alkaline pH going to a more neutral pH like pH 7, we see that you look at these kind of the main products of this reaction, and this is not quantitative graphs, but it does show the relative abundances of things that we've observed. You tend to see that in the reduced and alkaline situation, you make a lot of the alpha hydroxy acids. You make some amino acid, but mostly glycine, not as much alanine, and you kind of lose both of your precursors. But as you go slightly more oxidized with these minerals, it really start increasing the abundance of amino acids. So kind of in an intermediate oxidation state of iron, you get more alanine than glycine, and you just have a lot of amino acids in general relative to the alpha hydroxy acids. And when you go pretty oxidized, you actually have a lot of pyruvate left, and then some amino acid. If you start going to more neutral pH, you get different effects. So pyruvate is back. You get kind of a glycine-dominated system at the reduced iron, alanine-dominated at the oxidized iron, and then more lactate and glycolate throughout. So basically, when we're looking for organics on other worlds, or when we're trying to understand what kinds of peptides or polymers we could make, it's possible that these gradients and systems could really affect the relative or initial distributions of the monomers in question. But also that means that when we're looking for life, we can't really use organic distributions necessarily as a biosignature because the gradients could affect a lot of this. So at the very least, it deserves some further investigation. So maybe in a situation like this, you might be more prone to peptide formation if you have more amino acid. And or if you're in these kind of conditions, you might be more prone toward having these oligomers of the alpha hydroxy acids or the mixtures that was mentioned in the previous talk. And then we also we looked at the organics that are gone into the minerals themselves. And generally speaking, in these experiments, we see about half the organics go into the mineral, and they can't come out, and they're basically absorbed in there. So we did combustion experiments on these minerals, and we found about 0.4 weight% carbon. So that, if you look at what was initially in the experiment, that's about what you would expect. It's a best case scenario, but that's trace levels. So analyzing organics in a mineral sample like this would be pretty challenging. But you can kind of think about, what organics are in the sample versus in the liquid phase and what species might those be in. So in conclusion, in these abiotic or prebiotic reaction networks, they occur in these iron mineral systems, and it happens in kind of a short time scale, days to weeks, and it's under fairly mild conditions. There's nothing super crazy here. It's like 50 to 70 C, pH 7 to 10. And so we do see products forming. The organic products formed are stable in the liquid phase. We don't see these degrading or decreasing over time. And they could, in theory, if you had a porous medium like a sediment column or something, it could diffuse into other conditions in that gradient to continue to react. But there's also other organics that remain trapped in the solid phase. And the distribution of products that's formed relies very heavily on the gradients, in particular redox of iron, pH, and the ammonia concentration in this case. And so we see that highly reduced minerals tend to make more alpha hydroxy acids. Amino acids tend to be highest when you are alkaline and have high ammonia, but not all the way reduced, just semi-reduced. And there's also, I didn't have time to talk about, but there's other products identified here too that also exist in these systems. And so basically, when looking at alanine, lactate, glycolate, and glycine at least, these specific molecules have different maximum abundance conditions depending on the gradients that they're in. So perhaps that might have an effect on the distribution of these molecules in peptides or in oligomers. And it might be interesting to try to do polymerization experiments starting with these initial concentrations of things based on what environments we think it's happening in. So that's it. And I just want to acknowledge our lab group, the Origins and Habitability Lab, and in particular Erica Flores, who's the grad student who performed these experiments, and thank NASA and JPL for funding. If we have time, I can take questions.
Okay. So I'd like to start with a question. So I know that we talked about hot springs specifically. Is there any reason that you're invoking seafloor, or could this occur in any kind of geothermal environment?
It could certainly occur in any geo environment really that has a redox gradient. It doesn't even have to be that hot. So I mean, these reactions will occur eventually at lower temperature, it just takes longer. So yeah, it can be anywhere where you have iron hydroxide or oxyhydroxide precipitation in redox and pH gradients.
And would we expect those in hot springs?
Probably, depending on the spring.
Yeah, just curious. All right, first question.
Two related questions. Can you differentiate the relative contributions of your mineral grains acting as reagents versus acting as catalysts?
Yes, so they are reagents, not catalysts.
Well, but are they also catalyzing because of differential contributions there as well?
It's possible there's some catalytic activity, and we're still testing to see if that's the case, but generally I think it's stoichiometric with the iron, so I think it is mostly a reactant.
Nice. Second question is, your different mixtures of the input minerals were giving you different ratios of output products. Maybe you just answered my next question by the stoichiometry thing, but is there any evidence of grain-to-grain interaction?
It's kind of hard to tell, honestly, because it's a bulk system with such small particles. And so it is possible, though, because you could have things adsorbing and desorbing. We don't really see that, to be honest, with these molecules. You don't see a lot of decrease in the liquid phase, for example. But it's still something that we're looking into.
I think we'll go this way.
Hi, I think your synthesis of amino acids by reductive amination is a really interesting alternative to the traditional Strecker synthesis. And I was wondering, what is the prebiotic source of the alpha oxoacid substrates?
There's various ideas for depending which one you look at. And for pyruvate, it can come from CO or CO2 reduction on metal sulfide minerals, for example, but also both of them can come from meteorites. And so there's various ways you can get both. They can also they can be brought in as well.
Great, thanks.
Yeah, those are very interesting results. I assume that these reactions require minerals, and therefore they're going to be at the sea floor. And the point I'm making or asking about is that we assume that most of the iron in solution would be ferrous iron. So what reaction would pull enough of the iron toward the oxidized state to support that sweet spot you're talking about?
So it depends what what environment we're looking at, and it's not actually just the seafloor. So for early Earth, you're right, it would be a lot of ferrous iron, but you would have some ferric iron from reduction reactions with, say, nitrates and nitrites and other things. So you can get kind of, depending on where you are exactly in this redox system, you could get ferric minerals as well. But I'm also looking at this as, for example, in a Mars condition where you would have a lot of oxidation, and then also in surface environments where you go from the surface and then down below, you can have other oxidants, besides oxygen, causing that iron to oxidize. And sometimes you may not get all the way to the oxidized end of this, and so that's a possibility too, is kind of understanding where the environment limits you on the gradient itself.
Good morning, Dr. Barge.
Good morning.
Nice talk. I had a question, or I was hoping you could comment on peptide polymerization and what successes that you've had with that.
We have not attempted it yet.
And why not?
Well, we've been a little busy with this, but we will hopefully try to do some polymerization and also of the lactate and glycolate. That's been also done by other people, and so we would try to build on what hasn't been done specifically.
Okay, do you know off the top of your head how successful it's been in the other laboratories?
Well, I read a paper that was lactate and glycolate polymers. You make all sorts of things with that.
Okay,
So,
thank you.
yeah.
Great, let's thank Dr. Barge.